So the atom by itself, when there is no interaction, okay, has some frequency associated with it. Okay? And yet, nothing in the atom is literally moving in the sense of an energy density. Right? Does everybody get that? Because the eigenstates of the energy, right, they just change in phase as time goes on. So if you were to look at something like psi A of x and t squared, you would find that it's independent of time. Right? It doesn't move around. It's just one big thing. Right? A good example is you've got the zeroth harmonic of the atom, right? And that thing just goes womp, 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 but it doesn't really move, right? It just stays there, but it changes phase. And then what you've got, like another excited state, which is, or another harmonic, which is I'm going to think of the one that's an eigenstate of Lz. So this thing is like a donut, right? It also just stands still. It doesn't actually move stuff around. And of course, you know that that has to be true because that's exactly why people 100 years ago thought the atom should be unstable, right? And that's how radios work. If you swing charges around, they radiate, right? So these charges can't be swinging around. Does everybody get that, at least intuitively? Right?
So in a stationary state, then what's the frequency really corresponding to?
Exactly. So that's the question I would like to talk about, but it's kind of so. So suppose this is our state A, and this is our state B. Okay. Is everybody okay with that? So I am going to try to induce this transition by shining on the atom laser light, which has a frequency that matches the difference between these two. Okay. What is oscillating with that frequency? So now, what is moving at this frequency? That is the big thing we want to talk about. Okay, so if you have a classical mixture of two states, say B and A, okay, you know that, well, the state space would be represented something like a line segment. Right? And that line segment is just all kinds of mixtures you can have between B and A. So something that's up here is purely a B state. Something that's down here is purely an A state. And everything in between. So everybody see the picture I'm drawing. Right? So this is just all probability distributions of two outcome events. Okay. What makes this quantum, however, is that to every point there is now a circle. Right? There is a phase which is assigned to that circle. Okay, so instead of a point, everything gets a circle. Okay? And in fact, it's the most natural to describe this object as a sphere. Okay? And the point is that now, if I have any state, so this is my CA naught, this is my psi of t. Okay? What is it doing? In time, it is swinging. That phase is changing by exactly that frequency. So in other words, it's moving this way by omega naught. Okay. Does everybody see what I'm drawing?
Yep.
Okay. And can you see this makes perfect sense in terms of, you know that it has to be the case that the energy expectation is constant, right? And of course, all that means is that when these guys project onto the axis that you're normally considering, you get something that's not changing. Right? However, the state is actually processing around that energy expectation. Okay? And in what sense is this state real? Well, it's because there actually exists another observable, which is not this Hamiltonian, which will give you 100% that outcome. Right? Like when the state is pointing this way, then I could measure whatever corresponds to this observable. Okay? Different observable, H prime. And I'll get 100% one answer. This answer, say. Okay?
So, sorry. By this answer, do you mean you get that value of the phase shift of that mixture state?
No, when you make a measurement for a two-state system, you will get one of two answers, right? And that's the quantum nature. Is you say, what is your energy? You get one of two answers. What is your whatever other aspect I could talk about, which is a combination of these two, I will get one of two answers. Okay? I will usually get a random answer, or a random looking answer. That is, if I ask a question, which is for an observable, that the state is not an eigenstate. The point is that this is an eigenstate of some other observable, which means it'll give a completely predictable answer.
What's this?
The state, this. It is an eigenstate of another observable. Okay? Okay? So that's the really subtle part. This is the thing which is going around by omega naught. Okay? It is the actual possibility that you could have measured a different observable and gotten a completely predictable answer. That's what's dynamically evolving. Even though the energy density, or the distribution of the electron, is completely still. That just blows my mind every time. So, okay? So this is the thing you're actually matching. This is the dynamic which the light is resonating with. And that's like, if you can really get that in your head, you will be a lot farther than most people who do optics. That's very arrogant, some people who do optics. Seriously.
So I guess I don't understand the physical significance of H prime then. So if we take a step back real quick and say that omega naught is the oscillation of the probability that you're going to measure either like some mixture of state A and state B, is that okay to say?
No. You will get as a result either state A or state B when you measure the unperturbed Hamiltonian.
Okay.
When you make a measurement, there's more than one thing that can happen. And these are the quantum outcomes of that one observable, that one measurement you could make.
So what is the, I don't understand the significance of H prime then. If you could make some other measurement and it's not going to tell you anything about the mixture of A and B, or?
It will only tell you so much about the mixture of A and B. Right? I mean, it's again, if you are only measuring A and B, you can't tell what this phase is, right? So in a sense, this space of quantum states degenerates to the line, so every circle gets then assigned to one point. Okay. And every other observable behaves exactly in the same fashion. It can only see so much of this structure at once. In fact, there's a name for this. It's called tomography. If any of you have done classical tomography, it's a very nice name for it.
So when I look here, I look at the two endpoints of like pure A, pure B.
Yeah.
Those have radius 0. What should I extrapolate from that? What does that mean? Is there
It means there's no such thing as a relative phase between the A coefficient and B coefficient if one of them is 0. Right? I mean, if CA is 0, then I could have, right, this is just an overall phase. If CB is 0, then this is just an overall phase. Right? And it doesn't mean anything anyway.
So there's nothing to be in resonance with?
But you shouldn't think that this is the state. This is the electron. Completely holistically. Right? And each one of these circles is rotating at exactly the same omega naught. Okay, so it's like this quantum globe, which just rotates. Okay, but again, it's not a physical object. Right? It just rotates in a space of logic, in a space of possibilities. Possibilities in the sense that you can choose an observable, and when you choose that observable, this tells you exactly what happens when you measure for that observable's outcomes. Right. Okay, so I told you it's kind of subtle, but the point is something is dynamically evolving. Okay, even though the electron's density in actual space is not moving. Okay, both of which are crucial, because again, you can't swing charges around without radiation. So how is this thing evolving? It's evolving this way. Okay.